Hello, I'm going to be solving this chemistry paper today, February March 2023, variant 429701. New syllabus content has been added. Iodine is found naturally in compounds in many different oxidation states. Okay, iodide ions react with H2O2 to form iodine and water. So clearly, this is happening. Iodide is added to acidified H2O2 to produce iodine and water. So the oxidation number of iodine is changing from -1 to 0, and the oxidation number of oxygen is changing from -1 to -2. So oxygen is being reduced and iodide is being oxidized. Since iodide is, so what's the role of hydrogen peroxide? Okay, so since hydrogen peroxide is being reduced itself and it is oxidizing someone else, it is an oxidizing agent. Okay, so the role is an oxidizing agent. Okay, so next part, how are we going to balance this equation? Let's try balancing it. So we know that there's H2O2, we know that there's H plus since it's acidic, right? And we know that there's iodide, it's combining to form iodine plus H2O2. So our main goal, right, is to balance the number of electrons. So here the change is -1 to -2, that's 1 electron. Here the change is -1 to 0, that is also 1 electron. So in hindsight it looks balanced, right? But here's the thing, we know that there's iodine exists as a diatomic molecule, right? So we need 2 iodide on the left hand side, that's a must. So this is multiplied by 2. So to balance the number of electrons we also need to multiply the one below by 2. That's why we need 2 moles of H2O2 to form this compound. Okay, now what about the moles of water? How many do we need? How many moles of water do we need? Actually, we don't need a 2 here. We don't need a 2 here. There are already 2 moles of oxygen on the left hand side, 2 atoms of oxygen, and there is 1 atom of oxygen on the right hand side. So we know that since there are 2 atoms of iodine, the total change is 2 electrons for iodide, iodide to iodine. We also need to make sure that the total change for oxygen is also 2. Okay, but there are already 2 oxygen atoms on the left hand side, so we don't need to multiply anything on the left hand side, it's automatically balanced. We just need to multiply 2 here, right? And to balance H plus we need to multiply 2 here. So go for iodine first, then oxygen, then H plus. Okay, H2O2 plus 2H plus iodide is equal to iodine plus 2H2. So this is how I balanced it. I'm reviewing again. We had this equation from the beginning. So first I go for iodide 2, then I go for oxygen 2, now I go for H plus 2. This is it. Now we have partition coefficient, right? 15 cm cube of cyclohexane C6H12 is shaken with 20 cm cube of an aqueous solution containing I2 until no further change is seen. It is found that 0.390 grams of iodine is extracted into the C6H12. Okay, the partition coefficient of I2 between cyclohexane and water is 93.8. Okay, so since they're saying between cyclohexane and water, we need to keep cyclohexane on top. Okay, so the KPC is going to be like this. KPC is equal to iodine in concentration of iodine in cyclohexane, okay, dissolved in cyclohexane, divided by the concentration of iodine in the aqueous layer or water layer. Okay, so the KPC is 93.8. This is actually equal to So the amount of iodine extracted into C6H12. Okay, so it's 0.390 divided by, we don't need to convert the CM cube into DM cube, okay? Because the units are going to cancel out. Divide by 15. Now this is going to divide by mass left in the aqueous layer divided by 20. So solve this. What are you going to get? M by 20 into 93.8 is equal to 0.390 by 15. I'm getting a value of 5.54 into 10 to the power minus 3. Okay. In chemistry, we typically opt for 3 significant figure answers. Suggest how the value of Kpc of iodine between hexane 2-one and water compares to the value given in A2. Okay, we need to explain the answer. So iodine is mainly nonpolar. Okay, iodine is mainly nonpolar. So something that's nonpolar is more soluble in a nonpolar solvent. So just compare these two solvents. Cyclohexane is much more non-polar than water. As a result, iodine easily dissolves in cyclohexane as shown by this value, right? So if we used hexane 2-one instead of cyclohexane, think about it. How does the polarity of cyclohexane compared to hexane 2-one? Since hexane 2-one has an electronegative oxygen, right? It has a methyl ketone group. It's polar than cyclohexane. As a result, since it is more polar, less iodine would dissolve here, right? Comparatively, and as a result, the value of Kpc would decrease. Okay, that's the logic. Kpc, the value of Kpc would be lower or would decrease. Why is that? Because hexane 2-one is more polar than cyclohexane. Hexane 2-one is more polar than cyclohexane. That is the logic, okay? Or you could say hexane 2-one is polar and cyclohexane is non-polar. That is also fine. Now for the last point, we need to give a conclusion. So iodine is, or therefore iodine is less soluble in hexane 2-one. You need all 3 points to get 2 marks, okay? If you wrote 2 from here, you'd get 1 mark only. And if you just wrote 1, you'd get 1 mark, okay? Define the enthalpy change of solution. The enthalpy change when 1 mole of a solid dissolves in water to form an infinitely dilute solution or to form a solution of infinite dilution. One mole of solute when 1 mole of a solute dissolves in water to form a solution of infinite dilution. Really important, okay? It's also called an infinitely dilute solution, okay? Both work. Use the data in table 1.1 to calculate the enthalpy change of solution of potassium iodide. Okay. So let's make a Hess cycle. These are hydration enthalpies. And this is nothing actually. This is the direct route. So we had one route, right? Like we had solid KCl. We can go to, if we dissolve the solute in water, we can directly go to K plus aqueous and chloride aqueous. So this is the direct route, okay? Now there's an alternate route though. If we have the gaseous ions, right? we can opt to go here, aqueous form. That's called the enthalpy of hydration. Okay, this is given. We have this info. The one for potassium is -322. The one for chloride is, oh, this is iodide, by the way. My bad, guys. This is iodide. That's -293. Okay, so what about this other value? What is this -629? We can't call it the enthalpy of formation, right? Because potassium and iodine are not in their usual state. It's just a random enthalpy for the forming the ionic compound, right? So what is this? This is an enthalpy of formation, but it's the formation of ionic lattice. The energy released when 1 mole of ionic lattice is formed from its gaseous ions under standard conditions. So this is the lattice enthalpy, right? This is del H lat, which is -629. So just follow the arrows. You have this route where you go with del H sol -629 is equal to -322 plus -293. So if you solve this, you're going to end up with your answer. The answer is +14 kilojoules per mole. Okay, so it's the trend in the magnitude of lattice energies of group iodides. So guys, think about it. If you go down the group, what happens? Charge remains the same, but size increases, right? Charge density actually decreases. So cationic charge density decreases from Li plus to K plus, right? Now what happens? So lattice energies or enthalpies become, less negative or less exothermic. You could use an alternate. No, you had to say this as well, because there is less attraction between ions. Okay, that's all. Every point had to be included. Next, the concentration of copper in a solution can be determined by reaction of copper ions with iodide. Interesting. The iodine produced in reaction 1 is titrated against a solution containing thiosulfate. This is important. We use starch as the indicator, right? So a 25 cm3 portion of copper solution reacts with an excess of iodine. Okay. So the iodide is in excess. We have some residual iodine left. So we're going to titrate the residual iodine with some thiosulfate. Okay, the endpoint of the titration occurs when 22.3 cm3 of 0.15 mole per dm cube thiosulfate is added to the residual iodide. Okay, so here's the thing: thiosulfate actually reacts with iodine. So I'm going to explain this titration, what happens in that titration using iodine. So basically, you guys know that iodide is colorless, right? However, iodine is a brown liquid. So when copper 2 plus or anything in fact reacts with iodide, which is a reducing agent, the solution is supposed to turn colorless, I mean brown. However, we see that the solution does not turn brown. Why? Because thiosulfate is present in the solution. Thiosulfate, like immediately after this iodine is produced, what thiosulfate does is it converts that iodine to iodide. Okay? So immediately after iodine is formed, thiosulfate converts the iodine produced to iodide. That is why we do not see the brown color, because iodide is colorless. However, at the point when S2O3 runs out, right, the iodine can no longer be turned into iodide and the brown color is seen at the end point. Okay, so we add starch as the indicator because it gives a blue-black color. It is added at the end of the reaction. Okay, calculate the concentration of copper in the original solution. Okay, so first the moles of thiosulfate is 22.30 by 1000 into 0.150. That's 3.345 into 10 to the power minus 3. That's good. Now, what about copper? So hear me out. The ratio of thiosulfate to iodine is 2:1. So the moles of iodine should be half into 3.345 into 10 to the power minus 3. Okay, now look at this. The molar ratio of iodine to copper is 1:2 again. So what's the uh, number of moles of copper going to be? Half into 3.345 into 10 to the power minus 3 into 2. So this 2 and 2 are getting, we can cut them off, right? And we end up with this value, 3.345 into 10 power minus 3. However, this is not our answer because we need concentration. The concentration of copper is going to be 3.345 into 10 power minus 3 divided by 25.0 by 1000. Okay, that's all. So we are getting a value of 0.134 to 3SF. Okay, 0.134. Identify a suitable indicator for the titration. I was telling you guys, it's starch. It is added close to the endpoint to get a distinct color. So they want a 3D xy orbital. We know that the orbitals are going to pass between the x and y axis, okay? Between the x and y axis. So it's going to be drawn like this. Okay, this is one. And the other is going to be like this. Okay, this is 3D xy. Write equations to show how Fe3 plus catalyzes this reaction. So Fe3 plus is the catalyst, okay? So it has to be used in the first step since we need to regenerate it. So this is memorized, right? So 2 Fe3 plus 2 iodide. So in the first step, iodide becomes reduced and it oxidizes iodide to form 2 Fe2 plus and 1 mole of iodine. What happens in the next step? The same Fe2 plus ions, they actually react with persulfate S2O8 2 minus ions to form 2 moles of sulfate ions, okay? They reduce persulfate and in the process they regenerate the iron 3 plus ions. This is it. Okay, very important equations. If they told you how Fe2 plus catalyzes this reaction, then we would need to interchange the steps. Okay, now an orange precipitate of HgI2 forms when Hg2 plus ions are added to potassium iodide. The solubility of HgI2 at 25 degrees Celsius is 1 into 10 power minus 7. Calculate the KSP. So HgI2, guys, it forms an equilibrium Hg2 plus and 2I minus, right? So what's the solubility product? It's actually Hg2 plus into I minus whole square, right? So the solubility is this. So what does that mean actually? The solubility 1.00 into 10 to the power minus 7. This is also going to be 1.00 into 10 to the power minus 7. However, this is going to be 2 into 1.00 into 10 to the power minus 7. Got it? So let's do this. However, there's a catch. There's a catch. I did not do something beforehand. This is in gram per dm cube, okay? So we need to find the concentration in mole per dm cube, the solubility. So let's do this. Solubility of HgI2 in mole per dm cube, that's going to be 1.00 into 10 to the power minus 7 divided by, what's the AMR? 454.4. Okay. We're getting a value of 2.20 into 10 to the power minus 10. Okay. So this is actually 2.20 into 10 to the power minus 10. Also 2.20 into 10 to the power minus 10. This is 2.20 into 10 to the power minus 10 into 2. Okay. So let's find out the KSP. That's 2.20 into 10 to the power minus 10 into 2 into 2.20 into 10 to the power minus 10 whole square. Okay. I'm getting a final value of 4.26 into 10 power minus 29. And the unit is gonna be, since mole per dm cube thrice, mole cube dm to the power minus 9, okay? Pretty straightforward. First question done. So why is the entropy change of reaction 1 positive? Think about it. We are getting a gaseous compound. Solids are turning into gas. That's why. So 1 mole of liquid and 2 moles of gas are formed from 3 moles of solid. Or you could say that 2 solid compounds are converted to a liquid and a gas. That also works. Reaction 1 is highly endothermic. Suggests the effect of an increase in temperature on the feasibility of this reaction. So guys, check this out. Typically for endothermic reactions, if you increase temperature, feasibility increases. Why? Think about it. Del G is equal to del H minus T del S. So if del H is positive and del S is also positive, what's going to happen? Del H remains the same, right? And if you increase temperature, the value of T del S increases, the magnitude, and there's a minus sign before it, right? So in general, del H becomes more negative. Do you guys get that? So feasibility actually increases. So as temperature or T increases, T del S becomes greater than del H. Or you could say T del S becomes more positive. Okay, next step. So feasibility increases, or feasibility will increase as del G becomes more negative. Okay, that's it. Silicon is purified by first heating it in a stream of HCl to form SiHCl3. Okay, we have some entropy. Let's find out the entropy, right? This is the del S system actually. So products minus reactants. 314 plus 131 minus 3 into 187 minus 19. This variant is quite easy, honestly, till now. You could get full marks till now. 314 plus 131 minus 3 into 187 minus 19. We're getting a value of minus 135. So del S is negative, which is bad. Okay, next. Reaction 3 is the reverse of reaction 2 and is used to obtain pure silicon. So since it's the reverse, think about it. What is del S gonna be? Del S is gonna be plus 135 for this reaction. Now use this information and your answer to B1 to calculate the temperature at which the reaction becomes feasible. So when T is equal to 0 basically, right? I mean del G is equal to 0. That is the point at which it's on the verge of becoming feasible, right? So we know that del G is equal to del H minus T del S. Also, since it's on the verge of becoming feasible, del G is actually equal to 0 at this point, okay? So 0 is equal to del H minus T del S. This is a common question. Del H is equal to T del S. So temperature is actually equal to del H by del S. So let's convert the units. Del H is going to be 219.3 kilojoules. Since it's in kilojoules, we need to convert 135 as well. So that's 0.135, okay? So what's our answer? 219.3 divided by answer. I'm getting a value of 1.62. 1.62 Kelvin. Wait, did I mess up? Yeah, I did. Sorry. 219.3 divided by 0.135. I'm getting a value of 1624. Okay, 1624.44. So that is actually 162023 SF. But they aren't rounding it off. Okay, for some reason they aren't rounding it off. they're writing 1624 or 1624.4. Both are accepted. I guess for these types of, they should have accepted actually. I'm not really sure why. But 3 significant figures is safe most of the time, okay? Keep it in exact form, it's fine. Silicon can also be produced by electrolysis of SiO2 dissolved in molten calcium chloride. The relative half equation is shown. Calculate the time in seconds required to produce 1 gram of silicon by this electrolysis using a current of 6 amperes. Okay, so the redox reactions are not provided anymore. If they are relevant, they will be shown. And also the periodic table is attached to the sheet now. You can't use the data booklet while solving this, okay? So let's start. We know that Q is equal to IT. So Q is equal to 6.00 into time. Oh, we don't know the time. That's what we're supposed to find. Okay, cool. So 1 gram of silicon, right? Let's find out the moles of silicon. Why is it so big? The AR of silicon, is 28.1. AR of silicon is 28.1. Okay, so what's the moles of electrons gonna be? 4 times this, right? They have a 1:4 molar ratio. Now think about it. We know that Q is equal to IT. So how are we going to convert this to coulombs? Think about it. Q is equal to IT. Also, to find out the total charge, we know that this is the moles of electrons. 1 mole of electrons has a charge of 96,500. Faraday's constant, right? So Q is going to be 0.1423 into 96,500 charge of electrons, coulombs, right? Into current into time. Let's find out time. I'm getting a value of 2289.4 seconds. Okay, so 2289 seconds. For some reason, they're keeping the value in exact form. I'm not sure why. They should have accepted 2290. Okay, so they're keeping it to full form. Is it written in the beginning? Not really. So this is a new trend. Next, titanium is a transition element. Define transition element. We know that a transition element is a D block element that forms one or more stable ions with incomplete D subshells or incomplete D orbitals. Okay, cool. So we need to identify two properties of transition elements. They have physical, okay, just properties. Okay, variable. They have variable oxidation states. They behave as catalysts. They form complex ions or complexes, and last but not least, they form colored colored compounds or ions. Okay, so you can write any two. The compound, the ion TiO2 plus ion forms when TiO2 reacts with an excess of sulfuric acid. TiO2 plus can be reduced by zinc metal in acidic condition to form purple solution containing Ti3 plus. TiO2 is a colorless ion. Why? Okay, so usually transition metals do not form color compounds when they have no electrons in their d orbitals, or if you know it's full, like in copper 1 plus. Okay, so let's check titanium out. Where is it located? Titanium is here. Titanium is here. So it has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d2. So when we form the Ti4 plus ion, what happens? 1s2, 2s2, 2p6, 3s2, 3p6. That's it. These 4 electrons are gone, right? So it actually has an empty d orbital, so it cannot be classified as a transition. This ion at least can't be considered as a colored complex. All right, that's what we need to understand. Okay, so Ti is in 4 plus. See this oxidation number? Oxygen is -2, titanium has to be +4. Ta is in +4 oxidation state, so no d orbitals, or you could say d0. Okay, or you could just say that Ti in TiO2 plus has no d electrons. Okay, so what's the issue? Basically it cannot absorb photons or light in visible spectrum. Okay, that's the issue. Or you could say that no wavelength or frequency absorbed in visible spectrum. So what's the configuration of Ta3 plus ion? It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, okay, 4s2, 3d2. This is what was supposed to happen. But what happens when we form a transition metal ion? The 4s electrons are lost first, 2 are lost from here, and 1 will be lost from the 3d orbital. So it's going to be 3d1. Okay, write an ionic equation for the reduction of TiO2 plus by zinc in acidic conditions. So we need to add H plus. What's the product? We form Ti3 plus, and we form purples. Okay, so we form Ti3 plus. Okay, and thing is, guys, so zinc is reducing TiO2 plus. So zinc is going to be oxidized itself in the process, right? And zinc only has an oxidation state of 2 plus. Remember that. It has no other oxidation state, okay? You don't have the data booklet, so you need to remember a few things, okay? And to balance the H plus and the oxygen, we obviously need water, right? So if you look at the transfer of electrons in zinc, it's actually 2 electrons, okay? 2. But what about titanium? It goes from +4 to +3. That's a transfer of 1 electron. So to balance it, we need to multiply it by 2. So there should be 2's here. Now to balance the oxygen, we need a 2 here, right? Straightforward. Anything else? To balance the hydrogen, we need a 4 here, okay? Hopefully you guys get it. Okay, so for part C, this is a new addition to the syllabus. Titanium 3 plus reacts with oxygen, and it is oxidized to form TiO2 plus. There has been a change in the number of electrons. It has gone from +3 to +4, so 1 electron was transferred. And oxygen is reduced in the process, 4 electrons are transferred. We want to find out the reduction potential of the titanium half cell. So for this, we need to use the new formula that has been added to the syllabus. Del G is equal to -N E cell F. So how does this work? What do we need to ensure when doing this? We know that when del G is negative, the reaction is spontaneous, and when E cell is positive, the reaction is spontaneous. So think about it. If this is positive, it's multiplied with a minus sign, right? So plus minus equals to minus. So it makes sense. Overall, it makes sense. But we need to make sure of one thing. We need to convert the del G to joules. Okay, so it's going to be -436.1 into 1000 is equal to, what does the N represent? The number of electrons transferred, okay? -4 into E cell into the Faraday constant F 96,500. So solve this. I'm getting a value of E cell equals to 1.13 volts. Okay, now we need to find out the reduction potential of this titanium half cell. So we know that E cell has two formulas, right? It's either the reduction potential of the one that's higher minus the reduction potential of the one that's lower, or the reduction potential plus oxidation potential. So since we want to find out reduction potential, we should use the one on the top, right? So clearly in this equation, oxygen is getting reduced. So I am putting oxygen first. So E cell is equal to reduction potential of oxygen minus reduction potential of titanium, or 1.13 is equal to 1.23 minus that. So if you make that the subject, right, we end up with 1.23 minus 1.13, which is plus 0.10 volts. Hopefully it makes sense. Or plus 0.1 only, that's fine. Okay, no extra significant figures needed. Next, when aqueous saturated ions are added to titanium, this complex is formed. Explain in terms of d orbitals why is this able to form complex ions. Okay, think about it. So titanium actually has titanium 3 plus does have an electron in the d orbital, because look at the configuration, it was 3d1. So remember, when can you form a complex? To form dative covalent bonds with a ligand, you need to have empty d orbitals. Okay, if they're full, you cannot form ligands. Like zinc cannot form dative covalent bonds with ligands because all d orbitals are occupied. So you need empty d orbitals. So Ti3 plus has empty or vacant d orbitals. Okay, so they can form the empty or vacant d orbitals can form dative bonds, or accept lone pairs from a ligand. Okay, or you could say that the Ta3 plus has vacant d orbitals which are energetically accessible. That also works. Okay, asphyte titanium complex does not react with oxygen dissolved in water, unlike asphyte titanium 3 plus. That's odd. Although we have titanium 3 plus here, it's the same titanium, but it's just in the form of a complex. It does not react with oxygen. State what this means for the value of standard reduction potential. So hear me out, guys. Before it was plus 1.23, and this was the reduction potential of titanium, right? To form titanium TO2 plus H plus, plus E minus. I'm not giving the H plus. I think we had that equation given, right? We didn't have it. Okay, so anyway, basically this equation had a reduction potential. Wait, I drew it the other way around. This equation has a reduction potential of, I'm not balancing it by the way. It has a reduction potential of plus 0.10. That's why when we subtracted it, plus 1.23 minus 0.1, it was in fact feasible. It was a positive value. Now, when we form the complex, it doesn't really give us a feasible reaction. What does that mean? E cell is negative. So, think about it. If the reaction is not feasible, what does it mean? The value of reduction potential is greater than this. So think about it, it will be 1.23 minus a value greater than this, minus 1.30 for example. The value turns into minus 0.07. So it results in a non-feasible reaction. Do you guys understand? So the reduction potential of this, or the value of, E of the half cell, must be greater than plus 1.23 volts, or must be greater than the electrode potential of the other half cell. Okay, the oxygen half cell. Now some reactions of TiO2 are shown. The anion ACAC acts as a bidentate ligand. So what does coordination number mean? Oh, by the way, there was another thing that we need to mention in part 3, like the conclusion. As E cell less than 0 and the reaction does not occur. You didn't need to write this exactly. You could say as E cell is negative and the reaction is not feasible. That also works, okay? So what is coordination number? It is actually the number of coordinate bonds. Is the number of coordinate bonds being formed by the central metal atom or ion, okay? Write an equation for the formation of TiF6 2 minus from TiO2. It reacts with HF to do so, right? So TiO2 reacts with HF to form TiF6. So remember, if there's always extra oxygen, where does it go to? It actually forms water. It actually forms water. Now, how many fluorine atoms do we need? We need 6 to form TiF6. Now, if you think about it, if you try to give 2 here, right, what happens? You have balanced oxygen, but you're not able to balance hydrogen. You still have 2 residual hydrogen. So if you have residual hydrogen, remember, they can be released in the form of H+. There was another option though. You could actually balance this in this way. You could say TiO2 plus 6HF is equal to TiF6 plus 2H3O plus. That is also valid, okay? And TiF6 has a charge of 2 minus. So why was the H plus released actually? The 2H plus released. How were you gonna get that? Mainly because hydrogen was left. Remember, there was a remainder of extra 2 hydrogen. So we needed, and also electrical neutrality has to be maintained. The left side has a charge of 0, right? So the right side also needs a charge of 0. That's why we need a charge of plus 2 to balance it, okay? Really important. So state what is meant by a bidentate ligand. It is actually a species with 2 lone pairs of electrons that forms that form dative covalent or coordinate bonds to a central metal atom or ion. Really important definition, okay? So what about number 4? TiACAC shows both optical and geometrical. Remember, basically when you have 2 monodentate and 2 bidentate ligands, the compound can show both types of stereoisomerism, optical and geometrical both. If there are 3 bidentate ligands, only optical. If there are 6 monodentate, okay, then only cis trans is possible if 2 are different, okay? And if there are both present, 2 bidentate, 2 monodentate, then both are possible. Okay, so let's try doing this. Why don't we draw the trans isomer first? To draw the trans isomer, basically the chlorines must be along the same line, okay? So this is drawn in a weird pattern where we keep these 4 bonds in the same plane, okay? And the other 2 bonds, right? One is in front of the compound, the other is at the back. So let's draw the trans isomer first. Wait, I had to draw this better. Okay, so let's go for it. I'm going for the trans isomer. The chlorines need to be along the same line, right? And the ACAC has to be bonded here, like this, okay? That's all. Now for the other isomer, it has to be a mirror image of this. Okay, think about it. This isomer, right? This one over here, I'm going to show you a figure. Check this. It has to be a mirror image of this, right? So how do I draw a mirror image? Think about it. Think about it logically. Any mirror image works actually. It just depends on where you want to place the mirror. So we can do something rather than drawing the compound like this. Why don't I draw it like this? Check this. What if I draw it like this? If I draw a typical mirror image, we have these bonds in the same place, but what about this? What if this is placed here and this is placed here? Think about it, it becomes a mirror image easily. So we're just going to change the position, right? And put them over here. Like this. Now it's better. So we need to put the chlorines, look, at which positions? Mirror image. So like this, the chlorines will be placed here. What about ACAC? Think about where it was initially. One was placed here, ACAC. Okay, and this one was placed here, ACAC. Like this. This is it. As you can see, it's a mirror image, right? Laterally inverted. Okay, see if this is fine. I just drew the mirror image. It's drawn on top with the mirror. So the ACAC anion is symmetrical due to which if any of stereoisomers 1, 2, and 3 are polar. So you either have the option of saying isomer 1 or in my case isomer stereoisomer 2. Why is that? Because dipoles do not cancel, or you can say that partial charges do not cancel. That's why. Okay, next compound 4, we're starting with organic. Identify the other functional groups in F and J. Both contain arene. So F contains, this is a carboxylic acid, this is the amine group or the phenylamine group. So F contains phenylamine and carboxylic acid. Okay. What about J? It contains the phenol group and the ester group, right? It contains the phenol group and ester. Okay. Now let's go for chiral centers in F. So F really has no chiral center because these sp2 carbons cannot be chiral. This is also sp2, nitrogen cannot be chiral. What about J? These can't be chiral, right? This can't be chiral. What about this? This is clearly chiral. This is also chiral, okay? But this is not chiral since it has two same groups attached, okay? So we have two chiral centers here and 0 here, okay? The student proposes a multi-step synthesis of F from benzene as shown in table 4.1. Complete table 4.1 by providing relevant details of the reagents and conditions for step 1 and 4. Okay. So we want to produce methyl benzene from benzene. So what do we need? We just need CH3Cl, right? And the catalyst, aluminium chloride, right? You could say heat for Friedel-Crafts alkylation, but they didn't write in the mark scheme. Now we want to, we want to carry out nitration. However, you gotta take something into account. Okay, you need to take something into account. What is that? Basically, you have to think about the future. What happens in compound E? We are getting benzoic acid, right? That's happening later. So you know that the methyl group is ortho-para-directing. Usually it goes here, right? Ortho or para position. You need to make sure it goes to the para position, because compared to this, it's at carbon 2, 3, 4. It's at carbon 4. So when you draw this compound, right, you have to ensure that your nitro group, the NO2 group, is at the para position. Okay. And in step 4, what's happening? We're converting nitro group to the amine group. So we need tin and concentrated HCl plus heat. Okay, that's fine. Okay, for the next part, we have this. In a second multi-step synthesis, the student changes the order in which the reagent conditions are used. The reaction scheme is shown in figure 4.2. Okay, so G is the major product of this synthesis. How does this differ from our previous reaction? In our previous reaction, we had the methyl group over here, right, which is ortho-para-directing. So the nitro group would either go into the 2 or 4 position, right? However, now when we're producing compound G, we have the COH group in the ring initially. So how does this differ from that scenario? We're going to end up with a compound that is going to have the nitro group in another position, either the 3rd or 5th position. Why is that? Because the COH group is electron withdrawing in nature, right? And it is meta directing. You need to say that, okay? So you either put it in the 3rd or 5th position, counting from COH, and you need to say that it is it is an electron withdrawing group, and it is meta directing or 3,5 directing. Okay, this is the answer. This is the major product. Okay, next. So in part C, what do we have? J reacts under suitable conditions with NaOH. After acidification of the reaction mixture, compounds KNL form. Okay, so J is a compound with an ester linkage and a phenol group. It reacts with NaOH in 2 ways. Okay, so the NaOH will react with the phenol group, the one I've circled, to form a salt, right? And you know that phenols react with alkalis. And alkaline hydrolysis of the ester bond will occur. After acidification using HCl, we return to the phenol and the carboxylic acid. So what about compound L, guys? After hydrolysis, we know that on the right hand side, we're going to end up with, after hydrolysis, we're going to end up with an alcohol on the right hand side, right? So if I draw compound L, it's going to be like this. This is the compound L. OH. This is compound L. Okay, what about the number of hydrogen atoms? Since we need the molecular formula, let's find this out. Let's find out the carbon number. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbon atoms. What about the number of hydrogen atoms? We have 1 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. This hydrogen is the 18th one. So why did I not consider a hydrogen here? Because that carbon already has 4 bonds attached to it, okay? And it has 1 oxygen atom as well. So C9H18O. And what are the 2 types of reactions that occur? Alkaline hydrolysis of the ester bond and acid-base reaction or neutralization reaction between the phenol and sodium hydroxide. K can also be synthesized from phenol. Okay. K also undergoes 2 other reactions, one with sodium metal and one with bromine. So we know that phenol reacts with bromine to produce a white precipitate, right? And phenol also reacts with sodium. Acid plus metal is equal to salt plus hydrogen gas. So let's write this down. So phenol plus sodium metal is equal to sodium phenoxide, right? C6H5O minus Na plus and hydrogen gas. To balance it, it's going to be half H2. and it reacts with bromine to produce the white precipitate 2,4,6 tribromophenol. Okay. Explain why phenol is a weaker acid than K. So K has a carboxylic acid group. Why is phenol weaker than that? Let's try to understand. So phenol is a stronger acid than alcohol. Why? Basically, the lone pair of the phenoxide ion takes part in the delocalization of the benzene ring, right? As a result, it becomes more stabilized. However, what happens in the carboxylate ion is that mainly COH, the OH is attached to an electronegative carbonyl group, CO, C double bond O group, right? So it actually weakens the OH bond, which facilitates the release of H plus. Also, the carboxylate ion anion is stabilized by the presence of this electronegative oxygen. Okay, so two reasons add up to this. The COH bond is weaker, or you could say it is more easy to donate H plus in K. Why? Owing to the negative inductive effect, or the electron withdrawing effect of the carbonyl group. And for another point, for 2 marks, you need to write down the third point, which is the carboxylate anion is stabilized by the presence of this electronegative atom. Okay, so 3 points in total. In COH, the OH bond is weaker owing to the electronegative or electron withdrawing carbonyl group. It also stabilizes the carboxylate anion more than the phenoxide anion. Okay, comparatively, this is more stable, much more stable. Phenol and benzene both react with nitric acid as shown. However, and you know that benzene requires concentrated H2SO4 and concentrated nitric acid, right? Phenol does not require that. Why is that? Because phenol actually activates the benzene ring. What does this mean? Or what does this indicate? Mainly the lone pair of electrons on phenol, on the oxygen of phenol, actually takes part in the delocalization of the benzene ring. Okay? It takes part in the delocalization of the benzene ring. So think about it, the ring becomes more rich in electrons, so it becomes an easier target for electrophiles. Electrophiles can easily attack the benzene ring since it's much more negative in nature. So the first point is the p orbital on oxygen overlaps with the ring or the pi system. Or you could word it in this way, the lone pair of electrons on oxygen is delocalized into the benzene ring. Or the p orbital on oxygen overlaps with the ring or the pi system. Now the electron density of the ring actually increases. So it attracts electrophiles more easily or better, or polarizes electrophiles better. It's an easier target for electrophiles essentially. These are the 3 points. Now let's move on to 5. So this is 2-chloropropanoic acid, which is a weak acid. An equilibrium exists when it is added to water. So 2-chloropropanoic acid plus water is equal to the carboxylate anion and protonium. Okay, so our next goal is to find out the pK of 2-chloropropanoic acid. How? To find out pK, we need Ka because pK is equal to minus log Ka. This is our end goal. Now, to find out Ka, we need the H plus concentration, right? How are we going to find that out? pH is equal to 1.51. So minus log H plus is equal to 1.51. H plus is equal to 10 to the power minus 1.51, which is 0.0309. Now we know that Ka is equal to H plus whole square divided by the concentration of this acid, which is 0.150 moles by 250 cm cube or 250 by 1000. Now if you simplify this, we end up with Ka is equal to 0.0309 whole square divided by 0.60. You have to use your calculator answer to get to the final one, which is 1.59 into 10 to the power minus 3. Now if you use minus log Ka or minus log answer from your calculator, you're going to end up with 2.80. It's actually 2.798 or something. It's rounded off to 2.80, okay, to 3 significant figures. So an equal concentration of aqueous Right, so an equal concentration of aqueous propanoic acid has pH 2.55 compared to 2-chloropropanoic acid. It had a pH of 1.51. So what are we seeing? 2-chloropropanoic acid is stronger due to the lower pH and higher H plus concentration. So that's what we wrote in the first point. Now we're going to explain this. Why is this so? Due to the presence of that electronegative or electron withdrawing chlorine atom, right? It weakens the OH bond or stabilizes the carboxyl anion. Okay. So hear me out. You need to say 1 point here, 1 point only. But in this question, we needed more details. Okay. So depending on the question, you have to answer. It's safe to write both though, according to this mark scheme. So we have alanine and amino acid. We get this when 2-chloropropanoic acid reacts with ammonia. So alanine is one of the 20 amino acids. Its isoelectric point is 6.1. What does this mean? It's the pH at which alanine exists as a zwitterion, or you could say that it is the pH at which a molecule has no overall charge or becomes neutral. Is that clear? So to answer the next question, give the structure formula of alanine at pH 2. How are we going to do this? Mainly we need to learn something. I'm going to teach you. So at the isoelectric pH, the amino acid has both charges. Now the amino acid acts as a buffer. At a lower pH than the isoelectric point, like a pH of 2 or something, H plus is in excess, right? So what's going to happen to the excess H plus? It's going to be taken in by the carboxylate anion, so it's going to turn into COH, but there will be no change to the NH3 plus cation, okay? And at a higher pH, what's going to happen is there is a deficiency of H plus. So the amino acid will try to lower that change. How? By releasing some H plus into the environment. So NH3 plus becomes NH2. I hope I could clarify. So at lower pH, the amino acid tends to get a positive charge, and at higher pH, the amino acid tends to get a negative charge. Okay, that's why we end up with CH3CH N plus H3COH. You could write NH3 plus though as well, but this is what they want in the mark scheme. This is the new mark scheme, okay? Now we know that alanine has a chiral center. Okay, so the first amino acid, glycine, is the only amino acid with no chiral center, okay? So we just drew the optical isomer. You need to draw a mirror image, okay? Just like this. It has to be laterally inverted or you won't get marks, okay? See how I drew the COH, it's laterally inverted, the NH2 as well. And suppose the carbon here, it has to be attached to the bond, okay? Remember that. So a polymer forms between alanine and 4-amino-butanoic acid. So both of them contain carboxylic acid groups and, amine groups. So obviously they're going to form an amide bond, right? How is this possible? How are they forming an amide bond? Mainly because they can lose one molecule of water to do so, right? A condensation reaction will occur. Draw a repeat unit of C. The functional group formed should be displayed. So I put alanine first. This is alanine, and this part is 4-amino-butanoic acid. So I use the amine group of alanine and the carboxylic acid group of 4-amino-butanoic acid, and I put the dangling bonds on both sides. Okay, for repeat units you need to show these dangling bonds. Also this bond should be displayed. Okay, the rest of the compound could have been in a structural form. You could do this, I guess, CH2 3NH. That's fine, you would get marks, but I just opted to go for this. Okay, everything is fine, anything works. Okay, but the peptide bond must be displayed. There was another alternative, by the way. You could also draw this compound. You could do this. Wait up. This was also fine, okay? No worries, you could do this. This also works. Any one of these, okay? So what is the type of polymerization shown? This is obviously condensation polymerization. right? And scientists are investigating C as a replacement for polypropylene in packaging. Why? We know that polymers, additional polymers, are not usually degradable, biodegradable, but C is. It can easily be hydrolyzed. That's why we're doing so much research. A student studies the reaction of 2-chloropropanoic acid with aqueous ammonia to determine the reaction mechanism. Okay, so the student finds that when CH3CH, ClCOH, and NH3 added in a 1:1 stoichiometric ratio, the conjugate acid and base of the reactants are quickly formed. So what's the first pair? 2-chloropropanoic acid is the acid, and this carboxylate ion is the conjugate base, the anion. And ammonia is the base, while the ammonium cation is the conjugate acid. Okay, these are the two pairs. In an excess of NH3, the carboxylate anion basically undergoes a nucleophilic substitution reaction. Okay, a student investigates the rate of reaction 2. The student mixes the carboxylate anion with a large excess of NH3 so that virtually the concentration of NH3 doesn't change. We only want to see how the rate changes when the concentration of the anion changes. Okay, this is what we're seeing. Use the graph to show that reaction 2 is first order with respect to CH3, CHCl, COO. Okay, how can we do this? Mainly using half-life. Okay, so initially you have a concentration of 0.02 0.021, right? This 222324. Okay, so what's half of that? 0.021 by 2 is 0.0105. 0.0105. So this is 0.11 and 0.105 is over here. So it's basically here, kind of like this. It's around 500 or 520 seconds. Okay, it's approximately 500 actually, if you think about it, because it's actually intersecting the graph here, right? So it's approximately 500 seconds. Now to prove that it's first order, we need to show that half-life is approximately constant. Okay, so half of 0.0105, what is that? It's 5.25 into 10 to the power minus 3, or 0.00525. Okay, so this is 0.006. So where is 0.00525 gonna be? This is 0.0055, so 525 is gonna be here, 1/4 of that. So we are hoping that this is gonna be at 100, approximately at 100, and it is. It is exactly at 100. So the half-lives are constant at 500 seconds. So it is actually half, first order with respect to the carboxylate anion. So they want evidence on the graph, and you can say that T half is equal to 500 seconds. So since half-life is constant, first order. Okay, that's all. Explain why large excess of NH3 needs to be used. Very important question. I was expecting this. Mainly we want it to be virtually constant, so that it doesn't affect our reaction. We want it to be virtually constant so that the concentration of NH3 is, they're using the word effectively constant, so that it doesn't affect rate, or so that it's zero order with respect to NH3. Okay, that's the logic. We don't want it to affect the rate of reaction actually, since you can't actually find out the rate for two things at the same time. That's why you need to keep one thing constant and investigate the other one. Okay, the student measures the effect of changing the concentration of NH3 on the rate of reaction 2. Okay, now we're keeping the carboxylate anion stable and changing the concentration of NH3 plus. Okay. So let's find this out and then determine whether it's SN1 or SN2. That's fine. So using experiment 1 and 2, think about what happened to the concentration of NH3. When concentration of NH3 increases by how much? 0.00450 divided by 0.00300. How much is that? 1.5x, right? Rate increases by 2.21 divided by 1.47. How much is that? Also 1.5? Yes, also 1.5 times. So it is first order with respect to concentration of ammonia. Okay. Now think about it. What is the overall rate? Rate equation. Rate is equal to K NH3 first order, also the anion first order, right? So in total, the order of the reaction is 1 plus 1, 2. So if it's 2, I mean, I'm going to teach you now that it's, 1 plus 1. If it's 2, if the rate depends on the concentration of both the reactants, then it's an SN2 reaction. Typically, primary halogen alkanes undergo SN2. Okay, and one more thing. If it was an SN1 reaction, rate would only depend on the halogen alkane, not ammonia. Okay, so SN2. Why? Because rate is first order with respect to 2-chloropropanoic acid and NH3, both of them. Since it's first order with respect to both of them, the overall order is 2. Okay, that is why it's SN2. Okay. Describe the effect of an increase in temperature on the rate. So if we increase temperature, we know that rate increases, right? We need to explain this answer. So it's explained in terms of a Boltzmann distribution. What will happen? Greater proportion of particles have energy greater than or equal to activation energy, okay? And frequency of effective collisions increases. Or you could say rate of collisions. Rate of collisions increases. So rate increases, okay? That's the wording. Why is when an excess of 2-chlor the carboxyl anion is used, further substitution occurs. One product has the formula C6H9NO42 minus. Suggests the structure of C6H9NO42 minus. This is important. So what you guys need to understand is what is occurring here. Nucleophilic substitution. If you use ammonia in a closed vessel, nucleophilic substitution can occur multiple times. Okay. So what happened initially? So first we had CH3, CHCl, right? COO minus. What happens initially is that NH3, right? NH3 with the lone pair, it actually takes the place of this chlorine and we end up with this CH3CHCOO minus NH2. This is the first step after first substitution. So what's gonna happen next? So this compound, the one we got in the first reaction, it can act as a nucleophile, right? Because ammonia, this amine group has a lone pair. So this amine group, it can further attack one more 2-chloropropanoic acid anion, So it can attack this electron deficient carbon and take the position of chlorine. So what do we end up with ultimately? Check this. This is what we end up with. CH3CHCOO minus NHCOO minus HCH3 and see if the molecular formula matches. We have C6O4 1N and 6 7 8 9 hydrogen atoms. So this is it. Okay, so they don't want the mechanism. The mechanism would have been like this, the one I'm drawing, right? What do they basically want? They want the final structure that I drew on the right hand side after double substitution. Also guys, triple substitution could take place as well. Its substitution will keep on going as long as the nitrogen has hydrogen attached to it. Okay, I hope I could clarify. So let's draw the compound. COO minus CH3 NH CH3 COO minus, or you could go for skeletal. Skeletal also works. COO minus CH3 NH COO minus. Okay, both work. Your call. Last question now. This has a total of 14 marks. Okay, so lidocaine is used as an anesthetic. A synthesis of lidocaine is shown in figure 6.1. Okay, W can be formed by reacting OHCH2COH. So basically we're forming an acyl chloride with excess AsOCl2. Write an equation for this reaction. What is seen after this reaction? Mainly AsOCl2 is thionyl chloride, right? So white fumes of HCl will be seen and another colorless gas is formed, sulfur dioxide. Okay, so let's draw this. HOCH2COOH plus thionyl chloride is equal to Cl. Chlorine basically takes the position of OH. CH2 COCl. So remember guys, this is very important. Both alcohols and acyl chlorides react with thionyl chloride, okay? And both of them replace the OH group basically in the carboxylic acid as well as the alcohol. So we get an halogen alkane as well as an acyl chloride, right? Plus SO2 plus HCl. This is what we get typically when thionyl chloride reacts. Now to balance this, we need 2 chlorine atoms, which we already have. But think about it, there's another chlorine atom here. So how are we going to balance this? Mainly we need more Cl. How can we do this? By multiplying a 2 here and a 2 here. Now chlorine is balanced. We have 4 on the left hand side and 4 on the right. To balance sulfur dioxide, we need another 2 here. This is it. After W and X have reacted together, excess W and X, right? The acyl chloride is reacting with this aniline, phenylamine compound to form an amide. Okay? Only the acyl chloride part can form the amide though. An excess of sodium ethanoate is added to the reaction mixture. Why are we adding sodium ethanoate to the reaction mixture after W and X have reacted? So think about it guys, why is that? Mainly when these two react, right? Check this. What is formed actually? One molecule of HCl is released for each condensation that occurs. So HCl actually amounts to H plus, right? H plus. So the solution becomes really acidic and some steamy fumes are seen. So why are we adding sodium ethanoate? You know that this is the conjugate base of ethanoic acid, right? So it's a strong base. So that the ethanoate ions can actually take in the H plus. Alright. So it is done to remove or neutralize excess H plus or the acid produced by the condensation reaction to react with any acidic byproducts, okay, like HCl or even SO2. SO2 is an acidic gas, right? Or to react with any unreacted W, that also works. W is also acidic, right? It can also react with the with sodium ethanide. Okay, the reaction of W with X follows an addition elimination reaction. This is the new addition to your 2022 syllabus. Okay, this is really important. Both sigma bonds are produced and broken down in this reaction, as well as pi bonds. They are also broken and made again. So complete the mechanism of the reaction, okay, for addition elimination. Mainly what are we doing? What is the NH doing? It is taking the position of chlorine in this compound, okay? That's the main thing. You need to draw the lone pair on chlorine, right? And you need to show the dipoles properly. This is the dipole. This is del plus and this is del minus, okay? Now we're going to show the curly arrow. The lone pair actually attacks this carbon atom over here, right? And this pi bond breaks temporarily. That's the keyword. It temporarily breaks. Now what happens? So basically, since this amine group is attacking the carbon, we can't have the carbon, the carbon can't have 5 bonds at a time, right? So the bond temporarily breaks. Could I clarify? And the electron goes to oxygen and it becomes O minus with an extra lone pair, okay? Now we have our amine group attached, right? However, think about it. That like since this amine is attacking the carbon, it's giving away one of its electrons to the carbon, okay? So this amine below, it actually has a deficiency. It has a deficiency for now. Okay, this amine has a deficiency for now because temporarily it has given its electron to carbon to fill up that deficiency that oxygen took away from that carbon. Okay, remember, oxygen taking away one electron from carbon, amine fills up that deficiency temporarily. Now what happens in the last step? Ultimately, there will be a breakdown of this sigma bond. Heterolytic fission occurs. This chlorine takes away that electron, right? And oxygen, remember that pi bond we broke temporarily, we're gonna get it back again. The pi bond is made back again, we form it again. So carbon gets its rightful electron back, right? Carbon gets its electron back, and amine can take its electron that it donated to carbon temporarily. Okay, so everything has been reversed. What just happened? We just got rid of that chlorine. So some things happen temporarily, then we get everything back to normal. Okay, so this is it. Finally, we end up with this compound C double bond O, right? And here we have NH2AR, NH2AR. Okay, but there's a catch though. Basically, what happens here? That nitrogen, right? It isn't NH2 anymore. It isn't NH2 anymore. It turns into NH, right? So what happens actually? It's not like the nitrogen gets its electron back. I'll tell you why. Because even though oxygen is giving that electron it took in the first place back to carbon, right? Chlorine is taking away another one. So the deficiency always persists. The deficiency always persists. So what actually happens? This amine you see below, right? It actually lets one H plus go. It lets one H plus go, which combines with this Cl to form HCl as a byproduct. That's why we see some steamy fumes of HCl. Okay, so this is our final product. We're gonna get this CONHAR. This is it. Okay, and we have this. Okay, so in the process of doing so, one chloride anion was released and one H plus was released. They combined to form HCl gas, steamy fumes. Okay, so to get full marks you need to show this part only, very important. So C2H52NH reacts with Y in reaction 2. What happened here, guys? The halogen alkane, remember, whenever like halogen alkanes, their key reaction is nucleophilic substitution. So basically substitution occurred. Why is this acting as a nucleophile? We need to answer that, okay? Mainly, what are nucleophiles? Electron-rich particles, right? So, why is it acting as a nucleophile? The nitrogen, N or nitrogen, can donate its lone pair or LP or pair of electrons. That's it. That is why. Okay. Now we're almost at the end. The purity of lidocaine can be checked using thin layer chromatography. Ethyl ethanoate is used as a solvent. This is an ester. The RF values of X and lidocaine are given in table 6.1. Identify the substances used as mobile and stationary phases in this thin layer chromatography experiment. So remember, the stationary phase is always going to be a solid coated on the chromatography paper. It is either SiO2 silica or alumina, Al2O3 alumina. You can write any one, okay, any one works. And the mobile phase is obviously the solvent, ethyl ethanoate, okay, ethyl ethanoate. Describe how an RF value can be calculated. Interesting. So you should write this properly. RF is actually the distance traveled by the solute, substance, right, compound or component divided by distance traveled by solvent front. Okay, distance traveled by solvent front. Okay, suggest RF value of X is less than that of lidocaine. Okay, so guys, think about lidocaine, right? This is lidocaine. It is quite polar. It has a polar group. So mainly, when do you have this? If this is the starting point and this is the solvent front, so maybe lidocaine traveled up to here. It had an R value of 0.71, and maybe X traveled up to here, 0.49. So what does this mean? Lidocaine was more soluble in the solvent, basically. Or X is more attracted to the stationary phase. You could answer it in both ways. You can either say that lidocaine dissolves better in the solvent, or you could say that X is more attracted or has more affinity. X has more affinity or is adsorbed, okay, adsorbed more to the stationary phase. So remember, this is not absorption because it's a solid material which is forming intermolecular forces of attraction with the component. So it's adsorption. Now the proton NMR of lidocaine is shown. So they didn't give much marks from NMR this time. So name the splitting patterns at 2.6 and 1.1. So 2.6 and 1.1. 1.1 is a triplet and 2.6 is a quartet. Quartet and triplet. Next part. The relative peak areas of peaks 3 and 2.3 are 1:3 respectively. 3 and 2.3 guys. 3 and 2.3. 1:3 respectively. Okay, so hear me out. They are both, you know, singlets. So I'm gonna try to analyze this compound, see if you guys get what I'm doing. Check this out. Two ethyl groups, right? This actually means two ethyl groups. Okay, so how many environments are there? 1, 2, 3, 4, 5, 6. There are 6 environments. Let's try to find that out. How many environments are there actually? So these two, okay, I'm calling them environment 1 since it's symmetrical. These two, I'm calling them environment 2. This is unique, so this is environment 3, right? This is unique, this is environment 4. Now these CH3 groups over here, these are unique, so they are environment 5, right? And what about this benzene ring in total, in general? How many hydrogens are there? 3 in total, right? 3 hydrogens, because the other ones have been substituted. So these 3 environments, benzene as a whole, they're forming environment 6. So we got 6 environments in total. Now let's find everything out. Which one belongs to which? This is the important part, okay? So according to me, environment 1, it should have a triplet splitting pattern. Why? Because the adjacent carbons have 2 protons attached to them, okay? So environment 1 should have a triplet pattern. So there aren't much triplets over here, right? I think this corresponds to that CH3 into 2, okay? What about the quartet? How are we getting a quartet? 3 plus 1 is equal to 4. That's how we're getting the quartet. So I think environment 2, this is responsible. The quartet is the environment 2 is responsible for the quartet due to the adjacent carbon having 3 protons, and you guys know that 3 plus 1 is equal to 4, right? And remember this pattern. Whenever you see a triplet and quartet, it typically refers to an ethyl group. Could I clarify? So this is CH2 into 2. Next, guys. Next. What about this CH2 over here, the orange one? What should it be? No adjacent carbon has protons for that CH2 group, right? So what should it be? Think about it. Okay, I'm going to teach you something else, by the way. Basically, when you see a weird peak, when you say multiplet, right, that typically refers to the benzene ring. This is probably the benzene. This is the aryl group, hydrogens from aryl group, because it's so weird. Okay. Now, CH2, right? This CH2 should be a singlet. NH should also be a singlet. And those CH3s, the pink ones, they should also be singlets. Why? Adjacent carbons do not have protons. Okay. So you might be wondering, in the benzene, the adjacent carbons do have protons, but you can't consider them. Okay, it doesn't work like that. They actually interfere with they actually you know that when the proton is attached to an electronegative atom, right, like oxygen or nitrogen, it actually interferes with the resonance, so we get a singlet. No splitting occurs. Similarly, if you're attached to a benzene ring, right, and think about it, as CH3, what's your adjacent carbon? This one, right? This has no hydrogen attached to it. That is why there no splitting occurs. So we have 3 singlets. One due to CH3, 2 CH3s, one due to NH, and one due to CH2. So think about it. Which is attached to the most electronegative atom? Just think about it. It's probably the yellow one, right? NH. That corresponds to 8.9. And if you look at the booklet, if you're an alkyl amine, if it's attached to NH, or what is this actually? It's an amide, right? The NH is on an amide, CONH. The range is from 5 to 12, so this fits our criteria, right? This is probably due to, this singlet is due to NH, right? This is the yellow group. Now we need to figure this out. So they gave us a hint, right? The areas of the peaks, the area typically refers to how many protons are responsible for that peak. That's the peak area. From 3 at 3 and 2.3 is 1 is to 3 respectively. That means there are 3 times more protons in the chemical shift of 2.3, delta 2.3. There are 3 times more protons. So if we look at these two environments, we can actually come to a conclusion. The pink environment, right? How many protons does it have? The pink one, environment number 5, it actually has 6 protons, right? What about the orange one, CH2, orange? Environment number 3, according to my drawing, it actually has 2 protons, right? So look at this ratio. Isn't 6 is to 2, 3 is to 1, right? So now this makes sense. So which one is 3? Check it out. The one at 2.3, okay? So the one at 2.3 is the pink one, clearly. This is CH3 into 2. And the one at 3, the one which has less protons, right? That is actually this one over here. Okay? This one. CH2. Okay, so since I'm repeating it once more, right, with proper colors, The peak area of the peak at 2.3 is 3 times more than the peak at 3. What does this suggest? That the pink peak is at 2.3 since it has 6 hydrogens in total, right? CH3 into 2, 6 hydrogens in total. And the other one, the peak at 3, right? It has 2 hydrogens in total, so it's CH2. Okay, so that adds up. So now let's fill this table up. The relative peak area of the peaks. Okay, yeah. Identify the protons in the NMR spectrum of lidocaine. So the one at 7.1, the weird one with which is the multiplet, right? What do we need to write? Basically, look at this table. It's the aryl group, hydrogen attached to the aromatic ring. Okay, so you can just say hydrogen attached to aromatic ring, or you can just go for HAR. That's fine. HAR or hydrogen attached to aromatic ring. Okay. What about the one at 3? The peak at 3. The orange one, right? CH2. So if your alkyl group is attached to an electronegative atom like carbonyl, nitrogen, you need to mention that, okay? So since it's next to a carbonyl, we're going to mention that, and see, the range will fit that. The value will fit that range. So alkyl next to carbonyl, 2.2 to 3, it fits that chemical shift, okay? So it's actually, you can either say CH2CO, okay? Or alkyl next to C double bond O. Okay. Now for the last one, the one at 2.3, those are the CH3 groups attached to the aryl ring, right? So it's actually alkyl next to aromatic ring. Alkyl next to aromatic ring. Or you could just go for CH3AR, that's fine. Create the number of carbon 13 peaks in lidocaine. Okay. So why don't we draw or copy lidocaine again? I'm going to show you the number of carbon peaks due to carbon 13. This is the compound basically. We're going to do this carefully, okay? Step by step. So carbon peaks, step by step. These two, right? These are part of the same environment since they're symmetrical about the midline. So this is environment 1. These two are also the same, so they are environment 2. This is unique, so I'm calling this environment 3. This is unique, I'm calling this environment 4. Okay? What about this carbon? If we break down this compound through the midline, this one is unique, I'm calling this environment 5. Okay? Now, these two carbons, right? They are unique. This is environment 6. These CH3s, they're unique, so they're environment 7. These two carbons, they're unique, environment 7. I mean 8, right? I mean 8, since we used up 7. And the last but not least, this one. This is environment 9, last one, okay? It has no counterpart, so 9 peaks in total. Interesting question. So 9, the answer should be 9 peaks, okay? So that's all. If you have other questions, you can just ask me, okay?